So mechanical problems can be solved in any coordinate system. Maybe in rectangular coordinate system, spherical coordinate system, or cylindrical coordinate system. So we can write that mechanical problems can be solved in any coordinate system. In any coordinate system, say rectangular coordinate system, spherical coordinate system, cylindrical coordinate system. Arfken has discussed, Arfken, book by George Arfken, discussed 9 coordinate systems. So any mechanical problem can be solved either in any of them. But some problem is easier to solve in a particular coordinate system. As for example, central force problem. Central force problem can be easily solved in spherical coordinate system rather than in rectangular coordinate systems. It's better, easier to solve central force problem in spherical coordinate. So some problems itself requires any one of the coordinate system. It speaks itself that I should be solved in that particular coordinate system. Now we have, suppose I am taking here, we are considering only spherical and cylindrical coordinates or cylindrical coordinates. So in rectangular coordinates we have 3 axes, 3 planes, x, y and z. The position of any point can be described by the distance from these planes, and those are called coordinates. So this is the position of point. This is from here, from this plane, from this plane, and from this plane. So the coordinates are denoted as x, y, z. This x distance, its component along this is x, y, and z. Similarly, the position of a point can be described by taking one fixed point. This is the one fixed point, and the position of this point, say P, can be described by this distance. Now this distance, this r, can anywhere in the space of fixed distance, of fixed length. Suppose this is O and this is P, and this fixed distance is r. It can be anywhere in this sphere. So we have to take another straight line, and this angle will fixes its motion in a circular plane. Now if you take another plane here, suppose we have taken this plane and this straight line. So the pattern, so we have taken, so this is the angle. So if you take r, theta and phi, this will fix the position. This theta has fixed its position, so that if theta is fixed, suppose this is the straight line and this is the theta. Now it can, this is the r distance, now it can be anywhere. Now you have to, if you have fixed from this plane, the angle, so the position is, so in spherical coordinate plane, we have 3 coordinates r, theta, phi. In rectangular coordinates, we have x, y, z. Now we can transform from one coordinate system into another coordinate system. One can transform from one coordinate system into transformation from spherical to rectangular coordinate system. So suppose this is the fixed point and this is the R. So, and the angle which this makes with the z axis, so it is theta, and its component which this makes with this, the angle which it makes with this plane, say it's phi. So the coordinates of this point is r, theta, phi. So the x component of this, if this is r and this is theta, its component along z axis will be r cos theta, and here it will be r sin theta, and the component of r sin theta along x axis will be r sin theta cos phi, and the component along y axis will be r sin theta sin phi. Because the angle here is phi, so it cos of this is r sin theta, this length, and its cos is, so this is the x component. So x component is r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. So we have transformed from spherical coordinate to rectangular coordinate system. Now we can inverse transform. Inverse this first transformation will gives you r square x square plus y square, square this and you get r. Now to theta and to find it, we divide these two, you will get phi. So tan phi will given by y by x, and tan theta can be obtained by x square plus y square under root yz. Take the square of this and square of this. So it will be r square sin square theta will be common. Cos sin square phi plus cos square will be 1. R square sin square theta under root means r sin theta divided by r cos theta. That gives you tan theta. So theta phi is tan inverse y by x, and theta is tan inverse x square plus y square yz. So in this way we can transform from one coordinate system to another coordinate system, from spherical to rectangular and the inverse transformation. Now suppose spherical cylindrical coordinates. In cylindrical coordinates we have straight line, and the position of particle is given by the distance from this straight line. So if this is the position of the particle, this is the length, and this length is fixed. This length, we have to fix this length from here. So this is, suppose this is a from this plane, this makes an z distance, and from here it makes phi. So if this is rho, this is also rho, and this will be x-axis, y, and z-axis. The x component transformation from cylindrical to x will be rho cos phi, y will be rho sin phi, and z will be z. Inverse transformation. Take the square of these two, you will get rho. Rho will be x square plus y square under root. Take the find the value of phi, divide y by x, you will get phi is equal to tan inverse y by x, and z is equal to z. So this is the transformation. So here we can say in the spherical coordinates, we can say that x was r sin theta cos phi, y was r sin theta sin phi, z was r cos theta. Or we can say that x is some function of r theta phi. This was the transformation from spherical to rectangle. We can say that x is some function of r theta phi, y is function of r theta phi, and z is a function of r theta phi. Similarly, the inverse transformation we got r as x square plus y square plus z square. The root theta was tan inverse x square plus y square under root by z, and phi was tan inverse y by x. So we can say that r is a function of x, y, z. Theta is a function of x, y, z. Phi is a function of x. Similarly here, we can say that the x is a function of rho phi z, y is a function of rho phi z, z is a function of rho phi. So the coordinates of cylindrical coordinates related to rectangular coordinates, and in the reverse transformation we got phi. Rho is a function of x, y, z. Phi is a function of x, y, z, and z is a function of x, y. So it's just a preliminary of how to transform from one coordinate system to another coordinate system. Now, generalized coordinates. So what is a generalized coordinate? A free particle requires 3 coordinates to specify its position in space. Okay? And 2 particles, suppose we have one particle, it will require 3 coordinates, either in rectangular or spherical, or you take cylindrical, whatever, but it requires 3 coordinates. Either it requires x, y, z, or r, theta, phi, or you take any one of the coordinate system. So it requires, any free particle requires 3 coordinates for its position in space. Now if you have 2 particles, 2 free particles, 3 for this and 3 for this. So it requires 6 coordinates. Now if you have one more particle, free particle, if you have 3 particles, we have 3 for coordinates for this, 3 for this, 3 for this, so it will be 9 coordinates. Suppose we have n particles, free particles. Now the n free particles will then require 3n coordinates. So n free particles will require 3n coordinates to specify its position in space. So this is called the degrees of freedom. So n particles have 3n degrees of freedom. 3n degrees of Now suppose we have 2 particles, free particles, 3 coordinates for this, 3 coordinates for this. Now they are not free, but they are constrained to be within a fixed distance. The distance is fixed. Now the coordinate system will, and they are related, this fixed distance is related by one equation, separation equation. So now you will not have 6 degrees of freedom. If you fix 3 for this, only 2 will require to specify its position. So suppose one of the particles is fixed here. It requires 3 coordinate system. Now since this is the separation between these two is fixed, if this to fix the position of this point, we will require 3 coordinates. Okay. Now for this we require only 2 coordinates because this length is fixed. Either you take the angle from this any line, straight line, and from one of the plane, angle from another plane. If you take angle from this, suppose this angle is fixed, then this can be anywhere on this circle. Now you have to fix its position, you have to take the angle from this plane also. So it means it requires 2. 2 is required for this and 3 for this, so you have 5 degrees of freedom. Now if you have 3 particles, you require 3 to fix this one first, and 2 for this, and 1 for this, because all of them are constrained. And there are 3 constraints equation, one equation between them, one between them, and one in between them. So instead of 3 free particles, 3 free particles require 3 into 3, 9 coordinates. But if they are fixed by 3 equations, constrained by 3 equations. So their degrees of freedom is now is 9 minus 3, that is 6. 3, 2, 1. Here 2 particles, free particles, so 3 into 2, if they are constrained by one equation, which is minus 1, so it is 5. So it means if there are n free particles, they will require 3n coordinate system, and Suppose they are constrained by k number of equations of constraint. This is k. So the degrees of freedom will be 3 n minus. So n three particles. So we represent these Pn minus k coordinates, minus k independent coordinates. By 3n minus k independent variables. Say Q1, Q2, Q3 and minus k. Q may be anything. It may be XYZ, it may be R theta phi, it may be anything. So we have taken this as a generalized term, and that's why this is called, they are called generalized coordinates. They are general term. So these are called, these 3 and minus k are called, these are called generalized, these are called generalized coordinates. Now, as we have seen that we can transform from x rectangular coordinates to spherical coordinates as a function of r theta phi. So y is equal to a function of r theta phi and z as a function of r theta phi. Now suppose we have generalized coordinate as q1, q2, q3. We can transform it into another coordinate system. So one can transform from old one can transform from old coordinate system say R1, R2, R3, R3n minus k into generalized coordinate system. So Q1 is a function of R1, R2, Rn minus k, and so if time appears, you can take time also. So Q2 is a function of R1, R2, R3n minus k. We can take the inverse transformation also. Inverse transformation, inverse R1 is a function of Q1 into Q3n minus K R2 Hmm.